walking through the rules and like that.
All right, well, so first things first, the grading is all done and it should be posted. I was just checking in with Austin. So I think that's all good. I'm going to talk a little bit about a couple issues that came up in the grading in just a bit. But first of all, I just want to acknowledge that this is way late, and I know I've already promised to do this faster next time, but I wanted to tell you what specifically I'm going to do, so I'm not just making empty promises. Part of the issue was that I was reluctant to pass off the grading or some of the grading costs, and so I'm going to ask them to do more of the art grading this time around. So it should be more efficient this time. I acknowledge this was an issue, so has been consistent, I hope, throughout the course. If I see an issue, I try to do things to address it. So we'll do that this. You already know that the take-home was assigned on Friday. One little bit that I missed telling you on Monday that's going to be covered in the take-home. So there's going to be a little bit of philosophy of science because that hasn't been tested in a take-home context. So the kinds of things that you might expect me to ask are, I might give you a study design and ask you to evaluate it from the context of philosophy of science concepts. I could ask you to incorporate philosophy of science in one of those little write-ups that you do of a data analysis example, that kind of thing. It's not going to be too heavy because, it's already been tested, at least somewhat in the last in class. But I am going to incorporate something about philosophy of science in there. I'm also definitely going to test generalized linear models since we spent a good deal of time on that. So the sorts of things that came up in homework, so the sorts of things that are probably going to come up in the take-home. Lastly, we've spent a good deal of time on data management, and that's like very practical. So that's definitely the kind of thing that fits better in a take-home than in the main class. So you can definitely expect me to test that. This next drill with Austin, I'm going to ask you to do, or we're going to ask you to do an in-class exercise, a guided exercise, where you're basically going to get 30 data steps and you're going to quit. That's the kind of thing that you should expect me to ask you to do with the take-home. It's a little bit unfortunate that you didn't have an explicit homework yet on this. So for that reason, we're going to make sure that you have at least some sort of key to reference for the in-class exercise. So that'll give you some resources to pull off of. One odd thing about data management in general, I'm sure you've seen this as we go along, is that it's what we do really varies a lot depending on the context with data management, your specific scientific project that you're working on. And a lot of this stuff is it's hard to talk about in lecture. It's also, it's just really varied. It's been a little bit challenging to teach this unit. When I ask for feedback at the last, of course, evaluation next week after your take-home is due, that's something I'll be interested in feedback about is, was this useful, and what can we do to improve it? Finally, next week, we're going to start a pretty substantial unit that's going to take out the remainder of our time, actually, on repeated measures, or more generally speaking, data structures where you have multiple sources of error. That may not make sense right now, but hopefully it'll become clear as the next unit wears on. So this is going to be a pretty substantial, we're going to spend a fair amount of time on it. We'll consider a lot of extensions of, eventually we're going to talk about something called linear mixed effects models. So we'll consider a lot of different variations of these so-called mixed effects models. Any questions so far? So before we get to the topic for today, I did want to touch on a couple issues that came up in the grading. So I've already posted a couple keys. I tried to make them fairly detailed, so I'll ask you if you haven't already referenced it, please go back and look those over if you have questions or ask me by email. I guess there's not a lot of time before the take home, but I'm definitely open to questions early next week or on Thursday. So one issue that came up, this was a little bit small-ish, but it was a consistent issue across a lot of graphs that I looked at for the take home. And that's the labeling was a little bit inconsistent. So a lot of people said no.treat. And there was also an issue where the labels didn't match up with the graph with the groups that were displayed. So sometimes it went high.treat, medium.treat, and so on. The reason that happened was that I think either you weren't necessarily paying attention to the labeling to make sure that things matched up, or just didn't know how to change the labels. So there's an example in the key that shows you how to do this. Basically, if you create a new factor, the factor function gives you a way of changing the factor labels to the labels of the levels. In fact, it's called the levels argument. There's a levels argument which determines the order of the values will appear, and then there's another one called labels, which literally changes the labels of the factor. So if you're wondering how to do that, that's a great way to do it, using that factor function and changing either the order of the labels or what the labels show. An issue that came up with the write-up of this section was just not describing the multiple comparisons issue. That's something that I don't know. I can't say right now if multiple comparisons are going to come up later in the semester. I guess they could, because a lot of the stuff is cumulative. But although many of you noticed that there was a multiple comparisons issue in this problem, a lot of you didn't describe it in the write-up. So make sure you do that. And in fact, the p-values that you present ought to be the adjusted ones. So whatever you get out from p.adjust. A few of you had some issues actually implementing the p.adjust procedure. So I definitely encourage you to look at the key if that applies to you. Questions? All right. The second problem was definitely more complicated. Many of you either overlooked, or I'm not sure exactly what happened, but many of you didn't test this last prediction that the effects of the contrast will vary by pretest attitudes. Again, I'm not sure exactly what the issue was, but I wasn't too harsh with missing that little piece of information. But anyway, the prediction was there, and the models that you fed for, not for the manipulation check, but for attitudes post and discomfort, ought to have included attitudes free and interactions between attitudes free and the two contrasts. I was not too harsh with how I created the write-up, because I left it intentionally a little bit ambiguous what information you ought to have presented in the write-up. But a couple of things that I suggest you do if you have to if you have to describe a problem like this in the future. And again, I was not very harsh with how I evaluate these things. But including a table of the actual contrast values that you're using for your hypothesis tests that just makes it super obvious to the reader, like what it is that you did to pick models. So I find that very handy. I certainly didn't expect you were required this, but I do recommend it in the future. Another thing that sort of simplifies the description of this whole study is just providing a table of means and standard deviations. Again, didn't require it, but it's a good idea to do. The last point about this this problem was the figure. So I think this happened mostly because many of you missed the fact that attitudes free was the thing you paid attention to in the first place. But many of you did not incorporate anything about attitudes free in the figure. One option that would have been perfectly fine for displaying this figure is like a dot plot with maybe setting your predicted values, your predicted means at a particular value of attitudes free. So just showing one dot for the predicted attitudes post at the mean of attitudes free. That would have been fine if you did that, perfectly reasonable. Barring that, I think something like this sort of line graph, maybe with a vertical line showing where mean attitudes is, so that you can see, oh yeah, at the average, there's this, the discomfort per first condition is showing more discomfort. That would have been reasonable. But anyway, this is a very common way, not the only way, but a common way of displaying this kind of design. Questions on it? So like I said, I'm not sure how much these like kind of specific issues are going to come up in future take-homes. But there were a couple like, graphing is kind of more of a big picture idea that's, having good graphing principles applies to lots of stuff. So I think the graphing in particular, we did add on an extra day a couple weeks ago on graphing specifically, but this is another place that you can look for more ideas about how to implement these kind of graphs. Okay, so for the in-class, one issue that came up that actually affected how I graded this was that many of you, instead of doing dummy codes for this first problem, did something like a -1, 3, -1, -1 contrast, so plain orthogonal contrast. One of the key ideas to take away from this, like to tell whether you're in more of a dummy code situation or a plain orthogonal contrast situation, is that for plain orthogonal contrasts, you're specifically testing that all these groups are equivalent to each other. And in fact, that's what the residual contrasts are designed to do, is tell you, are those groups equivalent to each other? With dummy codes, you're not saying anything about how these extra groups relate to each other. So that's one of the key things to look for. Is the hypothesis a little bit ambiguous? And are you making specific commitments about, how all the groups relate to each other, not just one pattern or set of patterns? So that was something that came up fairly frequently. And I was pretty lenient about that. So I did not take off many points for that. The reason this affected the grading was that this last question didn't even make sense unless you were working with dummy codes. So I ended up just excluding it because I thought it wasn't fair, given, that was a fairly easy mistake to make at the very beginning, to use the plain orthogonal contrast rather than dummy codes. Another issue that came up was on this problem. This was a tricky one, so I'm not surprised that some of you got it wrong. That's all right. Just one big picture idea to take away from this problem. So you asked, like, what happens if you modify some of these groups? So if you bring this one up and this one down. Well, that right there is we're modifying the residual contrast. And the focal contrast, by definition, because it's uncorrelated with residual contrast, doesn't pick up any changes that happen with the residual contrasts. So that's kind of like big picture idea with this problem is if you do anything to work with residual contrast, it's not going to get picked up by the focal contrasts. So I believe the key for this has been up for a while. I'll double check that once I'm done. So I know I'm skipping past a couple things, and that if they may be of interest to you, please do consult the key or ask me questions. But one thing I wanted to highlight, because it's going to be relevant for the next take home, was this problem. Actually, people did pretty well with this problem, describing what this quote by Paul Neal means. A couple things that didn't come up, but it's maybe a little bit more specific to what might be an issue in psychology that I was not terribly harsh in my grading on, but they're just good points to note. Is that one of the things that might be special about psychology is this idea of crud. Everything is correlated with everything. It's like this background stuff that there's just a lot of variables that are going to be related to each other in the social sciences. And that can make it really hard to tell whether the fact that you see is the thing that you're interested in or crud. So that's like a big picture idea that didn't come up in a lot of responses, which was fine. But I just wanted to highlight that you could have talked about for this question. A lot of people got this idea that there's all these auxiliaries, all this stuff that's not related to the focal theory, but could be responsible for an effect that you see. That's great. You all did very well with that, and I'm very pleased.
Thank you.
Yeah. So I see some shock cases, maybe many of these problems were, you recognize me on them. Actually, I think the scores were quite good. And if you look at your grades, they're not low. And also, just to reemphasize something I said a couple times during this class, class is designed to be hard because I want you to grow and develop, and I don't push you away. So if you feel like you got some stuff wrong, that's fine. That's expected. I'm not expecting everybody to get everything perfect. And in fact, if there were a lot of perfect scores, I would think maybe I didn't make the tests hard enough. I want to see some spread in scores. So just to emphasize again, I actually think you all did very well. Part of this development that I'm seeing anyway, and I hope you're starting to see too, more comfort with R, better ability to utilize zeta, more understanding of what these concepts mean. Now I'm asking you to understand things at a pretty deep level. That's kind of atypical for this kind of class. So I'm pleased with that. Things are going. I hope that if you are feeling a little bit shell-shocked, I don't know if that applies to you, some reflections you can see. Actually, the fact that you were able to answer a lot of these questions is a really good sign. Any questions?
It's been a long time ago for me.
Yeah, like I said, that's definitely an issue, and next time we'll try to make the turnaround faster. right. So changing gears a little bit, or quite a lot. This is going to be our last class on data management. In many ways, I think this topic that we're covering today brings together a lot of principles that we've talked about at other points in this unit. And that is data accuracy. In general, you can think about, you can divide the reasons that data can be inaccurate into two different categories. Or you can think about preventing, or making sure that your data are accurate in two different ways. One is you can prevent the errors before they occur. And the other is that you can have some sort of procedure in place to detect them once they have occurred. So one is a little bit more forward-looking. The other you're doing after the fact. And in practice, you need some of both different types because it's hard to get for everything. But you also don't want to catch all the errors that happen after the fact because you might miss them. So in practice, you're going to be doing both of these things. The reason I said at the beginning that this unit kind of brings together a lot of different principles that we talked about earlier is that a lot of those principles, if you're doing good data management, if you're thinking about how to organize your projects, if you're thinking about capturing a lot of information in your project, metadata, and other stuff, well, that those principles are going to help you prevent errors. So being organized, that's one of the biggest things that you can do to make sure that your data are accurate and that errors don't create your data. So really big picture idea here. One reason to do data management in the first place is to ensure that your data is accurate. That's one of the biggest things that you can do, actually. That said, there are a couple other principles that you can use besides just like the stuff that we talked about. One is, so every time that you process your data somewhat, you transform your source data into your raw data or your raw data into your process data. Every step along that path is an opportunity to introduce errors into your data. Basically, something about that process can go wrong that can result in an error. In addition, each of those steps, going from the source data to the raw data to the process data, you can either use manual processes or you can use automatic processes. Basically, you can do it by hand, or you can tell the computer to do it for you. Manual processes aren't necessarily bad. Sometimes they're necessary. So one example that comes up a lot in my research is I often work with chunks of writing that people give me. So they could be essays, they could be those great reviews that I showed you. I work with that kind of data a lot. And sometimes you can use computerized tools to get stuff out of that data, but sometimes it's just a lot more straightforward to have someone read it and then read it once again. A coder basically, a coder who pulls out pieces of information from these chunks of text. That might be something that you all end up doing too. It's a very common method. Having manual coders isn't necessarily a bad thing, but it does have different implications for how error can enter into your data. Basically, if those coders make a mistake, it's probably not going to be a systematic mistake in that they make that same mistake every time this particular instance occurs. They always give a 1 instead of a 2. That could happen. But probably it's going to be a little bit more random than that. It's probably going to occur in one place but not in another. Whereas if you're working with a machine, a computer, almost by definition, if a computer makes a mistake, it's going to make that same mistake in the same way every time. In general, it's a little bit easier to fix errors if they occur in the same way every time, because you just call out all those different cases where the error could have occurred, and then you implement the fix. It's going to be the same fix every time. Whereas if you're working with human coders, if an error occurs, it's just a little bit harder to know what to do, or even to diagnose that an error is present. So, in general, my recommendation to you is to use automatic processes when you're creating your processing. It's not always possible. You don't want to do it in every case, but in general, when you're making sure that your data are accurate, automatic processes are just a little bit easier for you. Another reason to use automatic, like computerized processes, is that it's a little bit easier to document those processes. So often an automatic process involves like writing code and then executing that code. Well, that code serves as a record for that documents what happened in this process. If you have a little bit of commenting, it can be a pretty good record. You can have pretty good records for manual processes too. So one example might be if you have experimenters in a lab who do interactions with participants or whatever, you can ask them to keep written logs. That's a manual record of what happened. So perfectly, it's perfectly possible to implement some of this documentation with a manual process and should. But it's often a little bit more straightforward, I found anyway, to do that with automatic processes. Yeah.
You can do both at the same time, it feels like.
Yeah, so what are you thinking?
I'm not sure.
It sometimes comes up for me that I'm analyzing the same blocks of text. I do it in both a manual way and an automatic way. That, for example, if I'm trying to get counts of particular words or words in particular categories, I showed that to you in IH data. I might ask people to go through the text to pull out words that they think are related to research. I might also have a couple of categories of research words that I generated ahead of time. And that's to make sure that my automatic process is inclusive. It includes everything that's research related. It also excludes things that shouldn't be in there but might get swept out by the automatic process. So that's one example I can think of where I might do both.
I have a situation where I did both. I used R to pull tables into the giant table, and it didn't, and the image to text converted messed up on one particular file, so I just put that in my hand rather than trying to fix it.
Yeah, that's a really good example too. So sometimes it's hard to label your programs to do what it is that you need to do. A cost to mixing both manual and automatic processes is that, let's say that you find out that your source images have some sort of artifact that you weren't expecting at the time. Well, if you want to eliminate that artifact and then create your process data, you have to go through that manual process. Great. Whereas if you have a program that just is plug and chug, well, you just run it, and it takes 5 seconds, 30 seconds, however long it takes to do it. It's just a little more straightforward. So it's another reason why I tend to like automatic processes, but that's not to say that you should always use them. Sometimes it's just more expedient to go with the process. Actually, to finish my thoughts about prevention, um, what prevention, error prevention looks like really is going to vary a lot from project to project. In general, though, the things that you can do to prevent errors are the organized practice good data management and also be future looking. So I mentioned on Monday this idea of thinking ahead of time. How do you want your data to be structured, both in the source format, the raw format, and in the process format? How do you want your variables to be named? These decisions may look small, but they are the kinds of things that can streamline your processes, make them less error-prone, make them better documented, make them more obvious and transparent. So even though I can't tell you for your specific context, like this is how you should do things, that's more of like the big picture principle. Be future looking, think about how you want things to be structured ahead of time. That'll pay dividends. It saves you a lot of time. I know that from experience. Okay. That said, it's really hard to identify everything that you need to do ahead of time. You know, unexpected stuff happens. Errors happen. It's just inevitable. You probably heard of Murphy's Law. Everything that can go wrong will go wrong. Well, that's as true in research as it is in business. It's just the project has enough moving parts. Some of those moving parts are going to create problems. The big picture idea for how to detect errors that might be present in your data is to check for inconsistencies between different types of information. So in a second, I'm actually going to ask you to break up in small groups and discuss like what sorts of inconsistencies you can look for in your particular research contexts. But this is like the big picture idea is there are certain pieces of data that have to be consistent with each other or ought to be consistent with each other, or if one thing is true here, it has to be true in this other place. You look for those, and those can help you diagnose where your processes went wrong. Obviously, the more sources of data you have, the easier it is to do this. So some data, or especially metadata, you might record not because you're planning on analyzing it, but because you can capture some of this extra information that you can do to do these accuracy checks. In addition, you can think of the kinds of inconsistencies that you can generate as things that are just improbable. So you might know from past research that this correlation should be, you know, something, and it's not in your data. So what's going on? That might not necessarily indicate error, but it might indicate reasons to take a closer look. There's another type, though, where the inconsistency, like something has to be wrong here. So if you just know that this kind of measurement is not possible given the scale or the reaction time or whatever it is that you're working with. So what you're looking for, hopefully, is inconsistencies to the second type, because it tells you, you know, something is wrong here. You should also look at inconsistencies of this first type, though. You know, this is a pretty improbable pattern. It just doesn't quite make sense. Maybe I ought to take a closer look at the specific person or the specific group. Okay, so activity time. what this looks like is going to vary a lot from project to project. So what I want you to do is gather around in groups of, let's say, 3, and talk with your neighbors about, one, what are some possible ways that errors can creep into your data, the data that you are working with now or usually work with? 2, what are some of these future-looking things that you can do to prevent those errors? And 3, what are some ways that you can check for those errors? Either looking for inconsistencies that are improbable or inconsistencies that are impossible. I'll give you about 10 minutes to talk about this. I've got some ones that come up a lot in my area that might be helpful for you, but I'm first interested to see what kinds of things you can generate. So take about 10 minutes and we'll circle back and circle.
Or maybe machine learning, or even surrounding gardening, construction.
So in my view,
Check words, I guess, well, I think the best one's pretty,
Yeah,
It might be to understand. So it is hard, but there's something they need to do about taking
or maybe that's never.
because we have some people running the lab, some people have a language, yeah, a bit more, some people don't.
Sitting about like, maybe like 6 degrees.
Yeah, I think the perspective on having, making sure that being really, being about watching their data loss, especially in the beginning of the
Right, because they just started.
we can check for it because we'll see what. Correct.
Yeah.
But it might be, they're now looking at our data.
Just one thing.
Running the session.
Yeah.
So you remember when we wanted to get ourselves. I'm very,
Yeah.
jumbled up thing while these numbers. Maybe like circles, right? And then like so double checking is also that process.
Oh, yes, definitely.
Also too, takes like a lot of time, so don't make it sense. They're not. That's about 5.
Are you just making it? I have homework.
I work hard for that. We have, free test to make sure you know your name. And this is a click to show what.
Yeah, usually that's.
So we had an issue where we're doing trials in house, and then we're waiting for basically one people look at the trials now. And the RA is just gonna be shaky shop everything, so there's like a line where you can use this little bar over, and if you help it over the pressure, every little column. So it's neutral. Yes. All the way over, so cover all of it, there's like 100.00%. So then we was like, with just the front. That's not very cool. This is like a million and pounds. So that's like for that. So I just switched it from only one RA was doing it, and she was doing it really carefully, and then I checked the solutions would take time before I wasted time getting this on the board without it.
Yeah, I don't know why I'll research and I just sent email
One kid, I got the case under screen, my work, like I was trying to run outside.
I think it was his fault.
I guess like the over.
Yeah.
All right, I hear people starting to drift off topic, so this might be a good time to bring it back. Let's focus on this first question. So what are some ways that errors can emerge from your data collection process? Let's start with this group right here.
Well, it seems to me that one of the major concerns we have is whenever maybe you're not the one necessarily doing the collection process, so if you have an RA doing it for you, then they may not be trained correctly or etc. And so that could lead to some errors there.
Great, yeah. So can you give me some specific examples of how that might happen?
Sure. So yeah, with my cognitive test that I do, we get this output file of a bunch of reaction times, and they are not in any sort of neat, intuitive format. So what we have to do is we have to take a certain chunk of that data set, we have to move that to another data set, and then reorganize it and set it up in a way that we can actually use. And then so whenever you try to train someone to do it, and then rely on them to do it, making it very likely that a mistake is made somewhere in the process.
Susie. Another way that errors can emerge from the data collection process.
Another example for us is we have a task that's a bit confusing. I think it's confuses me to do it myself, so it confuses the RAs most likely as well. So they are supposed to be on top of emphasizing particular instructions to the participant, and sure the participant understands. We need them to get so many correct trials because we're interested in their brain activation during correct trials. So if the person doesn't understand the task and the RA doesn't know how to teach the task or check to make sure the task is being correctly answered in the task log, which happens sometimes.
Yeah, that's a good one. So confusing, very confusing instructions, maybe also not as much training on the like delivering the instructions as might be ideal, or perhaps a lack of clarity in that training process. Great, that's an example too. Certainly it's happened to me. Other ways that errors can creep into the data collection process. Let's hear from this group over here. So, what's one thing that we talked about?
So some issues that we have in a lot of the unmeasured cases is that we work with kids. It's kind of similar to what Morgan was saying. They can misinterpret instructions and they sometimes circle two choices of like the Likert scale item. So they have to fix that deal of how to figure out how to even record that data at all.
That's a really interesting example. That's an interesting one too, because I can imagine errors creep in either because of the instructions or because of the recording process. So if you don't have the standard way of dealing with those kinds of multiple circle responses, that can create confusion. It's really interesting.
Make it digital. They can always set
Right.
by much backgrounds.
It depends on the school's resources.
This is something that happened to me with one of my first projects. I wasn't working with kids. I was just like walking down the street, passing out surveys, and people would miss items, skip items, circle multiple numbers. So it isn't just a problem that happens with kids. And one thing I discovered was that one, my instructions were bad, and the code didn't. And two, on that last page, it was really easy to miss that there were complex items to complete. Just let you think about, fixes for that.
When I was in Dr. Hannah's lab, we would give these paper surveys to intoxicated people down on Dixon. There was a lot of mistakes that were made.
Yeah. So you have to be super clear for those participants.
Right.
That's cool. Other ideas about ways that errors can creep in.
Recording errors, for instance, my lab last year, you're supposed to put in a number for a participant. And for some reason, my RAs kept putting 1 and 1 and 1 and 1 and 1. So then they kept overwriting like the one participant. So we lost, I think, like 45 participants just from that error. We figured out only like halfway, so I guess prevented it. That hurt, it really did. Maybe preventing it was checking daily, checking if people are, is how many people are supposed to come in that day and see if it matches up how many participants we have that day. So,
Yeah, ongoing checks. I can actually think of a couple of things that might be causing that sort of error. So the experimenters might not realize why it's important to have different numbers, or they might be losing track. So I'm not talking about fixes yet, but I have some experience with this one. Some things that you could do might be to keep a log so that they can see which participant they're at. Another idea might be telling them why certain things are important, just emphasizing that during the training process. Another thing that might help is actually the software. So your software doesn't have to overwrite data if it has duplicate possibilities. That's usually something to change. So, software fix might help make that data recoverable. Other items?
Then when you're how things are stored, like where the data goes on the computer, and backing it up with so you don't lose the data, where there aren't multiple copies.
That's a really good one. So backing up, we talked about that on the first day. It goes back to this idea that a lot of these new practices help make data more accurate. Yeah, that's a great idea. Other items? We haven't heard from you guys. So what's one way that there's created?
I think we talked about like anytime your data from your data collection process has to be transformed in some way. So, I mean, one example would be if you're just collecting like text with answers, but you're converting those to numbers or something, then there's a chance that the capitalization or something like that switches it up.
Every data transformation is an opportunity to make another mistake and stays out. So one thing you don't want to have happen is for the change to be irreversible. So I haven't talked about this idea, but it's kind of important. So one reason I like, I think R has some nice features for thinking about how to do data analysis, and it's also quite powerful. But one other reason that's not quite obvious, so I liked it, is that when you're working with data in R, you're working with a digital copy of it. You're not modifying the data set that you actually read in. That's going to be a CSV file. So that means that if you make a mistake, it's not irreversible. And if you have worked with SPSS in the past, you actually load up the data set and modify the data set. That's one reason I don't like that way of doing data analysis, is that it's good to keep the separation between the original data and what you're actually working with your analysis. Any other thoughts about your code processes based editors would have?
Yeah, we had an eye tracker that sucked really bad. And it was super hard to get it to cooperate with the other parts of our system. So it was kind of like, I don't know if it worked, it didn't work. So it created some error in that way.
That's a tough one.
So we just did that.
Yeah, if the lab has the resources, might be time to replace that. Although if you're dealing with expensive equipment, it can be dicey.
It's new. I think it's just trying to get a bunch of things to cooperate across some of the platforms. You need the task and the eye tracker.
Well, that's a really interesting point. So we talked about how data can have a simplified structure. You might have multiple instruments that are recording the data, and then you have to merge the data. So lots of things that can go wrong with that merging process. Great. Okay, how about the second question? We talked a little bit about error prevention already, but what are some other ways that you can prevent errors? Some future things. Regular checks. Yeah, great. Allows you to see a problem early if there's a problem.
Piloting. Cards to checking it out.
That's a biggie. So piloting is incredibly useful. It's just like, sometimes you hear this term dry run. Dry run might be, ask your graduate student buddy to come in and do a task. I actually did this for several of my friends back at UW. I told the story about how I was just in a study where I got drunk and then saw pictures of death in porn. Not all of the studies are quite that interesting. The whole point of that wasn't necessarily to look at the data to see if the hypotheses were correct. It was just to see, is there stuff that's going wrong in this data collection process. I'd say that's the most useful purpose that pilot can serve.
Also, if RAs do the task that they're going to teach, that would be good. They can understand where the difficulties are or how the instructions are difficult for them in particular.
That's a really good one. Having people teach the process, other people who can do their observer might encounter problems that you didn't even realize were present. It's really good. Other items?
For me, I'd like to automate my data automation, so that'd be very handy.
Automation can save lots of time and it can be a preventative measure. You have to be a little bit careful. I sometimes have this tendency to like try to automate things that would be faster than to just do. But I've also been in a situation where I just decided, well, I'm just going to do this thing. And then I realized that there's error earlier on the data collection process. And I sort of press myself into doing it again, I think. Often anyway, if you think about automating early, you can make things a lot easier. This is a good list. Okay, what about this last one? So assuming that you can't make any changes in a future-looking way, what are some ways that you can detect errors once they're present?
Using graphs,
Correct. So can you take
like we do in R, just to see what the graph calls, if they're outliers or weird.
So you're thinking like histograms maybe, scatter plots. You see this one point and it's way separated from others. You even do formal tests for outliers. Look at studentized residuals. You remember way back from last semester, or leverage, or influence. It's good. Other things.
In our data, you can look, you know how many times someone has the opportunity to get something correct. So if they're not doing that even half of the time, then you know you can intervene like during the actual task, or just you can just look and see if everything's like that or not on a particular things.
Measures often have known properties, and this is information that I encourage you to record in, say, a code documents and work. One of the reasons to do that is that that information can be used to check for inconsistencies. So, for example, if you have a bunch of trials and you're looking at a number of correct, while that number correct cannot be less than 0. If you're getting that, then something's really wrong. It could happen. It also can't be greater than the number of trials that you have. Because something is really wrong. This kind of things happen. So it's worth checking or thinking about. But also, if the numbers aren't plausible, but they're very high, so about 50, 60, 70%, that might be another reason to check. So we're seeing some of this difference between inconsistencies that definitely indicate a problem, so the number correct is less than 0, or inconsistencies that might indicate a problem. So you just have a large number of inconsistencies. Great.
So just a question on that.
Other things. I think this question is a little bit harder to get a grip on. So I've got a couple examples that might help prime the pump a little bit. And I don't mean for this to be an exhaustive list, but these are things that I've found. So under improbable inconsistencies, the kinds of things that I often look for are, I've worked with a lot of longitudinal data, so people that come back to multiple sessions or multiple responses for probably the same people over time. If I measure the same thing at time 1 and time 2, so let's just say that we're measuring depression. If the relationship between the time 1 response and time 2 response is really low, say 0, or even negative, that could be just true, but it might also indicate that there's something wonky with the statement. So I'll tell you a story. For one of my first projects in graduate school, I took a data set that someone else had collected, so I had to do a lot of learning about this data. And I noticed something with the help of my advisor who had much more experience, kind of weird about the data, which was if I looked at a correlation table and looked at each measure correlated with itself, correlations were about 0, just across the board. So if you saw that, what might you think is going wrong? So depression, correlation with depression at time 1 and time 2 was about 0. Anxiety was about 0. These were the actual curves, but this is the kind of thing that's happening. So what do you think might be causing that?
It was incorrectly one time.
Incorrect version. So turned out what had happened was that participants were assigned different IDs at each time point. And when it came time to merge all those things together, just got a bunch of, it was just garbage. Not useful. Now, fortunately, the person who had done this study before, nothing, he's fantastic. He was actually an undergraduate, and he'd done this like really complicated study, and actually pulled it off. So he didn't do anything wrong, but this was a mistake because he didn't receive training on this stuff. But he had created enough documentation that I was able to sort of piece back together who was doing across time points. But it took me, I don't know, a couple months at least. It was a costly error, but recoverable. So that's one thing that you can look at is correlations. Sometimes correlations are just unreasonable. Or if a pattern is like really, really well established, you have to be careful here because you know, some correlations like they're just what happens, even if they're a little bit improbable. But sometimes it can be a reason to take a second look. Sort of a similar vein is if you look at your descriptive statistics and the standard deviations are either very high or very low. Where very means it's like around 0 or maybe just like outrageously high. So think for a second, what might be one thing that would cause a very high standard deviation? Could be an outlier. So this has happened to me recently. When I got this data set from a survey company, so I wasn't the person who was actually collecting the data. We had contracted the company out to do this. I opened up the data set and I looked at some descriptives, and I noticed that something that should have been on a 1 to 7 scale had some standard deviations of like, they were just outrageous. They were like 7. I mean, it just didn't make any sense. So I dug through the data a little bit, and I realized, oh wait, the survey company uses the code 99, the number 99, to indicate a missing response, someone who didn't respond. I didn't know that. It wasn't clearly documented, but I was able to, because I was careful and sort of looking through some of this basic information, I was able to detect that problem very early. Other things that occur to me are manipulation checks where it's just like an abject failure. I have to be careful here because sometimes that's the real pattern that might be a reason to take a second look. Already talked about outliers. This last one, I just wanted to mention because it's good practice to do this. So sometimes I mentioned like you ask research assistants to read through structured blocks of text and code out different things. One thing that you ought to do, but may or may not have known to do it ahead of time, is to have a second coder go through those same blocks of text and just go through the process again. That allows you to check the consistency between the first coder and the second coder. That can tell you things like, were your instructions clear? Or do you have one coder who's just a little bit sloppy? You can also like actually just diagnose actual errors. So someone may type of, this is one way to look for that kind of thing. So that general idea is called checking for reliability. It just means if you have a manual process, have the second person who go through the manual process again and check the consistency between the first person and the second person. You can also do it with a percentage of the data, because sometimes it's really effortful to go through these processes. You could do it with I might have mentioned my wife did EEG research in graduate school, and she did this with looking for EEG effect. Basically, someone moves and it messes up the electrodes. You have to make a decision: is this movement or is this something else? You want actually ideally two people to go through that same procedure to check that they're making consistent decisions. So that's a really big one that comes up in my work. The impossible inconsistencies, well, we've already mentioned actually quite a few of these. So we mentioned values that are just outside of what's possible on a particular measure. You might actually just do a quick check for, every value in this data set. Are there any values that are above 7 on a 1 to 7 scale? Those have to be errors. There's no other possible explanation. If you have to merge multiple data sets, you can check to make sure that the total number of rows at each merge is the same, or at least what you expect. That's a very handy one. Once you have a process data set, you can make sure that the number of cases in that process data set is not more than you expect based on, say, a code book or like a lab manual or something. Some sort of written record of what happened in each session. Sometimes comes up where an ID variable is not entered correctly by a research assistant. Actually, we talked about this too. Maybe you asked your research assistants to sum numbers, and there's a letter of multi-ID variables. Or all of the ID variables are single digit, except for one that has 3 digits. Probably the last one is ID variables that are not unique. So sometimes if we talked about how data sets can sometimes be structured where multiple ID variables in each row, where you have the same ID variable comes up, say, 3 times if there are 3 time points. So this one doesn't always apply. But sometimes if you're doing like between subject study, it just can't be the case that one occurs multiple times. That's probably a typo. There are more of these. There are lots of these. And the checks that work for me might not be the same as the checks that work for you. So a lot of the art of checking a data set for accuracy or integrity involves thinking about what ought to be true in kind of a creative way, and then using the information that you have to check whether those things are true. So it's kind of a creative process, actually. It's not one that can be easily manualized. I just do this the same way every time. There are also a couple extra tools that I want to make you aware of. Some of these are just functions that I use a lot in R when I'm doing these sorts of checks. And then there's one extra tool that you can use way at the back end. So among the R functions, there's like 3 sort of big picture categories that come up a lot. One is like, there are these logical operators that check whether certain conditions are satisfied. Another grouping is what's sometimes called munging. It's like ways of manipulating data. And then the last one is actual looking at statistics and seeing whether the statistics are reasonable. So among the logical operators, one that you probably encountered most of these, but one that you maybe have not encountered is in. What in checks for is whether the value in A also occurs in B. So you can think you might have a set of ID variables, one per data set. You can use in to check are all the ID variables in A also found in B? Or you can make it a little bit more complicated and you can say, give me all the ID variables that are in A that are not found in B. To see, like, was there a typo when you introduced or whatever. So I use in quite a bit. You can also use that to check for variable names, for example. All the variable names in A, the same names that are found in B. So it's extremely useful. Some of the munging functions, we've actually talked about two of them, gather and spread. That was last week. A few that maybe you've used often are filter and select. Filter gives you certain rows. So you can say, give me all the rows where the scale response was above 7. So that might be used to check whether there's a number that you don't expect in a particular variable. They can tell you to pull out just those rows where that happens. So that's also super useful. Allows you to look at the data to see what's actually happening. And last category, there are lots of ways that you can do this, so this is not meant to be exhaustive. But table, that gives you a table of frequencies. Tell me all the ID variables that occur twice. That's the kind of thing that you might do. Describe, describe statistics, correlations, whatever. This is not an exhaustive list. Sorry, any questions about this?
I'm not real sure what that person is.
So in tells you have a vector of things, like they could be names. So Patrick, Barry, George, whatever. So it's just a list of things. So you take that vector of things, and then you say for each of those names, are they also found in this other vector? So you could say for the name column in dataset A, are all the names that we see in that name column also found in the name column in dataset B?
Why would you want to do that?
If you're like merging data sets and you want to see ahead of time, like, can I use this ID variable as an ID variable? This can check for merge properties. It comes up a lot. I find myself using it a lot for various things. I mean, there are lots of potential uses. It's just a handy tool to have. So the other tool that you can use that occurs way at the back end, so this is like maybe once you actually have written the paper, is called StatCheck. You can think of it as a spell checker for your statistics. What it does is it looks for little statistics that are written in APA format, and it says, are the degrees of freedom consistent with the test statistic? And that's what it checks. So this is a way to look to find typos or other sorts of issues that may have led to a problem with your report. So I recommend that you use this. Once you've written your paper, you literally just upload it to that website. It gives you a table like this, and it tells you basically, are these test statistics possible? Just any way to prevent yourself from making mistakes. I won't go into this last session in detail because we're running a long time. But there's a lot of creativity that goes into looking at places, potential inconsistencies. Like I said, I don't think it's something that can be easily manualized. But actually, this idea of looking at inconsistencies is kind of an active area of research right now. There are people who are interested, like if you have a written paper, how can you look at the statistics that are reported in that paper to see if they make sense? So this is actually from the perspective of like detecting errors in other people's work, but it also can give you some ideas for ways that you can do error or anomaly detection in your own work. So this guy right here is a food researcher named Brian Lunsig. If you've heard of the study where you have a bottomless soup bowl and you supposedly eat more, if the soup bowl is bottomless, then it like automatically refills, and if they can see the soup bowl completely. Well, it turns out that study and others that he did are probably not real, or at least the evidence isn't there. And the way that we know that is through this process of anomaly detection. So I recommend that if you're interested in like learning more about this, there's a really good article in BuzzFeed that goes through some of this. There are a lot of blog posts about the researchers who look at these problems. It's just an interesting case study in how you can like look at different pieces of information to just check for inconsistencies, which can indicate errors or other kinds of problems. So just if you're interested, I followed this pretty closely. I actually met Brian Lunsig once at SPSB, so I had a personal connection. You might find it interesting too. Thanks very much, and I'll see you next week.